So the problem for today is the same as what we did 3 weeks ago now, before I took a break for vacation. And it is still to review changes to the model and make progress with the modifications if needed. And then what we also discussed is that we could spend some time identifying what are the policy areas that we may want to modify to start creating new simulations that we could then present in the shorter policy briefs. And for this, we may go through sector by sector or the key sectoral areas you're interested in for this policy analysis and identify what could be modified and how, and then what type of analysis we could perform. So these are the two main aspects or topics for today. I know that IBEC is not ready yet to present the modifications to the model. So if I understand correctly, Tatiana, you have made some more changes that we can review together. And then maybe after this, we can talk about the policy changes and the policy briefs. So can you share your screen, Tatiana, and then we go through the modifications either made or expected together?
So the things that I have added were mainly in the thermal capacity, because last time I did start this module, but we didn't finish. And so now the problem was mainly with the units and with the fact that the heat produced from coal boilers from population is not actually counted by our statistics like heat energy, like thermal energy. They don't count it. So we have a consumption of coal by population, but it's like we don't know for what, you know. Although it's quite obvious. I mean, this is for heating, but we don't have the amount of heat produced through this anywhere in our energy balance. I don't know whether that's normal or not, but you can see it here in orange. So as soon as I sort of excluded that, we did have somewhat of a fit. I did not include the historical, the time series yet. This is the value for the blue one. This is the value for 2019, 18-19. So, well, it's in the middle somewhere. And basically, this is the sum of all of the heat generated through cogeneration with coal, electricity, gas boilers, and crude oil boilers. I had to exclude these ones, as I said, because otherwise we have too much heat produced and it's not really with the statistics. And from that, we have the heat power loss, which is, well, somewhat of a fit here. And it mainly depends from the thermal networks and the condition in which they're in. It also, of course, depends on the efficiency of the boilers, but they are sort of here, they mentioned here. And I have to say, I've put very low numbers here because this fit the data. I know how much heat was produced from cogeneration, and so I had to sort of match it, and I used the efficiency as a calculated value for that. Then we have this additional demand for electricity used for heat, which is quite large still. I don't think this is quite right because, it can be. No, it cannot be because we have the overall production of like 15 M. And
this red line is the old simulation, right? Not the number 2. Right. So yeah. Probably, I guess you fixed it in the second one, I assume.
Let me just get rid of the red one so that we are not confused. Yeah. So this looks more like it. 1.5 billion. That's sort of a reasonable number. And then we have the conversion rate. Here I've had the actual losses, but I've disconnected them because we sort of counted them twice, in my own opinion. That's about it. I wanted to discuss how we can, I don't know whether we have to fix something here, and how we can connect this further to emissions and energy efficiency measures, or we just leave it here and just use it for, I don't know, for something else, not for the analysis. What would be your comments, Andrea?
Okay, so there are two aspects I think we can discuss in more detail. One is that all the inputs you have now are exogenous, right? They're not internally calculated. That is why you have a constant line for the heat produced, right?
Yeah.
So do you think it makes sense to make it endogenous, maybe driven by population or driven by decisions to expand the heat generation network? Or are you happy with having it external? Maybe just driven by a policy decision or so?
I'm not quite happy with it being external, but I cannot see whether we can have the data for that.
No, but besides the data, what are the sort of the factors that determine the expansion of production of heat? Is it the government is looking at population growth, is wanting to connect more people to centralized heat, or what are the main drivers for change in the production that we have now?
Well, obviously the population is growing, but the thing is that we have limited heat capacities at large thermal stations, and they are already, they're at the max already. So more and more people will be switching on to electricity, and this is why I had this here. The government, the overall policy is not quite clear. There are some talks about switching from coal to gas or boilers, but not quite clear. There is again the policy of, using local coal because we have it and it's cheaper, and there was a big switch to coal around 8 years ago because we had gas cut from our neighboring countries. There was like some political problem. So there was a huge shift to coal at that time, and we are still there. Apart from this, nothing much here. Well, it would be great to switch to electricity apart from the fact that we don't have enough electricity as well.
Okay, so it seems to me that instead of making it fully endogenous based on, say, population or so, it could make a policy decision where we have the desired heat energy produced as like an external policy target or goal. And then we have that driving the potential use of different technologies. And the use of technologies to reach that target could also be a policy, right? Do you want to use more coal, or do you want to use more electricity? Mm-hmm. Do you want to increase the efficiency of the boilers for the new capacity? Because in a way, it's like electricity, right? Where we have capacity. That capacity changes over time. In the electricity sector, it changes based on demand, and demand changes based on population and economy and prices and so on. But in this case, if it's most exogenous, it doesn't make sense to have a stock and flow structure for each technology, right? For cogeneration, for electricity, gas, boilers, and so on. So maybe it would be enough to say we have a policy to determine total generation, required generation, and then to have other policy variables to determine which technology you may want to use. Say in a baseline scenario, you may want to use coal. In a green scenario, you may want to use electricity or gas, for instance, so that we can have these policy variables to change assumptions in the various scenarios. Now, this covers the inputs, right? If that works, then we know we have inputs that are scenario-driven or policy-driven. But then the outputs, where do we use this information? Like the total heat energy produced, we have a few areas that we can use. One is we link it to total energy consumption and total emissions. Right? That is one aspect. And for that, we have the gas used, coal used, crude oil used, electricity used, the variables on the left that we can add to total energy demand to determine emissions. Then we may have the cost of generating heat, right? And so the economic aspect that could be added up to the total energy bill, potentially. Do you see any other area where we could link heat energy produced to the rest of the model, to other sectors, besides emissions and the cost of generating?
I think that would be, emissions and costs.
Okay. And both of them are connected to GDP, right? There's indirect impacts. The energy bill affects productivity, and also emissions affect concentration and then productivity. So they have impacts about the economy in any case.
Just a second, Andrea, I have to make Nurlan a translator here, which I don't know how to do. So we were discussing where to use the results. I think emissions and costs, energy efficiency somewhat.
There could be an intervention option to affect the energy use here, right? Jobs is another area. Like we have for energy,
yes.
We have the jobs per unit of capacity for the boilers.
Oh, I don't know if we have the data for that.
It should be similar to power generation, I assume.
It should be, but we have a lot of small boilers, which is like, I don't know, one person, two people. Like we have about, where did they have this information? Here, we have boilers. Total number, it's like Yeah, it's about 2,000 boilers. Even if we calculate people like, I don't know, well, the larger ones might have a larger employment, but not that many people. Actually, most of them are quite small and they are connected to public buildings.
So it's only maintenance cost, right, to keep it going.
Yeah, so I mean,
Maintenance
quite a lot.
Okay.
But the problem with them is that they are very old and very inefficient. This is the main issue.
Now, a quick point going back to what we used to drive the generation of energy, heat energy produced. You have now, and I'm thinking about how to connect this to the energy use and the emissions. So here in this case, for power, we have demand driven by population, GDP, and so on, that determines capacity by type, and we have a policy that we can use to decide whether we use renewable energy or not on the left side. And then this generates capacity, and then from capacity, we obtain the fuel use. In the case of heat, we have on the left side, we have the amount of energy used, and then as a result, with the efficiency and the conversion factors, we have the heat generated. So the starting point or the entry point for us is the energy used, right? So it's saying basically this is the input that we need to produce the heat output. Now, do you think that we can use, if we set a policy, do you think that we can affect directly the energy used, so coal, electricity, gas, or we should have a demand, sort of a demand variable, where then we apply the share of coal, the share of cogeneration, the share of electricity, and based on the share we identify, then the model tells us how much is the energy used for each of the technologies. So what I'm saying is, should we modify directly with our inputs the energy used as input, or should we modify a share of the total amount for each technologies so that then the model determines the energy consumed?
The point is that we have a strange system which is a bit left over from the Soviet times. Let me just show you. The point is that each year we have a special statement issued by the government which says how much of each fuel there should be. Let me just show that here. So, for example, they are planning how much there should be electricity produced. They are planning for each station how much coal should be used. They are saying how much. In part, this is driven by the government decision. So if they say, let's say, next year, to all related ministries and stuff, they say, okay, don't buy any coal this year. Let's just buy electricity. Then there sort of would not be any choice. At least for the part that is subsidized by the government, at least for the part for the municipal and stuff, you know. But for the population, in part, of course, they would be influenced by the unavailability of, let's say, coal. But then we have a market. You know, I really doubt that the government can actually stop all production of coal. They might, because they are subsidizing it. So if they say, okay, let's buy the whole amount of coal and make it available at lower prices as do now. So basically the population would then have to think what is better for them. And that of course would involve the decision of what kind of boiler they would have to install and what kind of cost of energy that they're going to use. So this is quite part and part. So maybe maybe the difference here, you see it with this orange one. So the rest, we might be, I don't know. So what do you think in this situation?
No, so I see two options, as you said. So one is, if we want to calibrate the model according to the historical trends and the statistics you receive, what you have done is perfect, right? Because you have the specific information about the energy sources used for producing heat. So if this is what you have also for the future, it's perfectly fine to keep what you have. If instead we think that it's not possible to have forecasts for the future and you have to operationalize the model somehow, then adding something like shares by energy source makes the simulation easier, meaning that you change one variable instead of changing six, right? Instead of changing each energy source use that you have now. Actually 5, not 6.
Share as a policy?
As a way to set up the scenarios, right? But that being said, I would normally use the share because it's just more immediate and it's easier to communicate and say, oh, 80% is coal or 75% is coal, rather than saying you use 10,000 tons of coal or 11,000 tons of coal. But on the other hand, I think what you're saying is right in that it's difficult to change consumption, I guess, especially for the population. Like if they have a coal boiler, a small coal boiler in the building, they cannot just put gas into the same boiler. They just have to change the boiler completely. And that is quite a decision that I guess doesn't come from one day to the other. So I think it's fine to keep what you have now. So the energy use as an input, and that is the one we may change to make so that we can generate new forecasts. So what I would do here, I would take all the variables on the left, coal use for heat cogeneration and so on, make them bold in orange, so that we remember this could be policy drivers, so that when we run a new scenario, we can change the actual amount of energy used.
So we're not doing shares?
No, I think it's fine to keep it as is, because then you have the full historical time series to compare with. So you can say, I want to reduce this or increase that. And just for you to know, for this task, if you use the hand and select the area with all the variables, you can select them all at the same time. If you select all 5 of them, yeah. And then at the bottom, don't right click, otherwise you fix one at a time. If you select all of them, okay, then at the bottom, you can click on the small b for bold, okay? And then on the first black square, that one is the color of the variable. Okay, so this way you can modify them all at the same time. It's a little bit faster.
Yeah, thank you.
Okay, so I think this is fine. So we know that when we want to run a new scenario, different from the baseline, we may want to change these parameters. Then one thing I also do, just for your information, is that if you have 2 clearly different scenarios, right? One is baseline, that is calibrated with a certain amount of coal use, electricity, and so on. And the other one, say the low carbon scenario is very different. Then what I will do is to copy paste these 5 variables on the left and add a switch called, say, heat generation switch. So that when the switch is 0, we use the business as usual variable. When the switch is 1, we use the low carbon variables. And this is for a simple reason. When you want to run the low carbon case, you don't have to manually change the values in each variable, but you only change the switch. So it's just to make it a bit faster.
Yeah.
Copy and then paste and then add low carbon at the end. So copy and then Control C on your keyboard and Control V, or there at the top. Yes.
Yeah, sometimes the things that don't work here in the same way. So.
And then suffix could be low carbon or something like that. Yes. Add a space before low. Otherwise, you see low is attached to the previous word. So if you do edit undo, you can redo it, or you have to change it manually.
It's just one. Okay, I'll change it manually. It's fine. And then we add the switch, which is...
The switch is a new variable. It could be heat generation switch.
Of orange, right?
Yes.
And then we connect it with all of those.
No, I would not link the switch to these variables. The switch should be connected to the heat produced for cogeneration, heat produced from electricity boilers, because that's where you have to decide whether to use one variable or the other.
Okay, wait.
So we can do the first one. Yeah, so link the switch to heat produced from cogeneration. And then also link coal used for heat generation low carbon to the same variable.
Okay.
Okay, so now in the variable for heat produced from cogeneration, we have to change the equation there.
Here.
Yes. So in this variable, we need to have, first of all, an if then else function. If the switch is 0, let's say, equals 0, then a comma, on true, we basically use the formulation you had before. Yes, okay.
Right.
If it's 1, so if it's false, you take the same equation, but you use the coal used for heat generation, low carbon. Okay, so if you do this for all the other ones, then you see that automatically when the switch is 0, you use the baseline formulation. When the switch is 1, you use the newly calibrated low carbon assumption.
Okay. But shall we do something with the population part, this orange part? Shall we leave them the decision? Or
well, you have the same assumption, right? You have the same assumption for the low carbon scenario. So that one will be modified as well. But what do you mean by should we leave them the decision? You want to moderate endogenously based on prices or something similar? Or
yeah.
Okay.
Or is it's not consistent?
No, I mean, you can use different formulations for different variables, right? So you can say that either you assume, if you remember, that in a low carbon scenario, the coal price will go up, say because of taxation.
Mm-hmm.
Then you would want to adjust manually this one to reduce the use of coal. Or you bring here the coal price, right, the relative coal price or something similar, and we use it in the equation.
Mm-hmm.
Either way is fine. But for now, do it in the same way, just for simplicity.
This might be made much quicker, I think, with superscripts, how do you call them?
Yeah, with subscripts, you make this change once only. Yes, instead of making it 5 times for the 5 energy sources.
But this is a bit confusing at the moment.
But the challenge with subscripts is that, let's say that you use 5 different equations, say 1 for population, 1 for the decision on coal, 1 for electricity. Then you have to introduce 5 different equations anyway. So subscripts work well when you have the same structure being repeated for all the components that you want to do.
But otherwise, it's like it looks really messy.
Yeah, then you can organize things a bit more in the screen, but yes, it's just a repetition of many of the same connections.
Okay, so for now we are leaving this. But I don't have that. No, yes, I do.
Yes. So for now, the formulation is fine. All you need to do is to add a value of 0 to the heat generation switch for now, so that it's operationalized and dimensionless. And then click on the other variables. Yes. For now, these take the same value as the other ones that you have. So we can keep them like this now, but when we run the low carbon scenario, we have to modify them. But at least we know that the model, if we fix these, the model now runs. There is no problem if you want to test other simulations. Okay, so if we were to say, do this or use this for one policy brief, let's say we want to change assumptions on heat.
We will discuss soon the things that we have discussed yesterday. I just wanted to ask some questions about that slide. So then we have that heat demand by population multiplied by population. And that would be, is it correct, Andrea?
Yes. So if you run the model now, your heat demand by population should have a similar value to the one you have in the orange variable, at least at the beginning of the simulation. Or if you use population currently for current year. Yes, for the current year, 2019. So now you have this dynamic formulation that shows that with the growth of population, you would have more demand for heat. But this is demand for heat that is unaccounted for. So you have to decide whether you want to assume that all new population in this case will be connected through independent coal boilers or not. So you may want to apply a percentage of the future value rather than the total number.
We have a maximum of capacity, which is like, yeah, I mean, if we talk about distributed generation, like city-wise. I don't see any kind of large cogeneration plants being built in the future. It might be boilers, like some for several houses, multi-apartment, for a rayon. Like we have several regions of the city that are served by smaller boiler companies. Whether this is state-driven, are they now state or private? They're now state, but I don't actually outlaw. I don't like any new house can have a boiler in basement or something like this. Then we need a projection of the in-city and the rural population, or maybe just look at the statistics, how many of them live in multi-apartment versus individual houses. And the last data we have for that is 2009. It's just not...
But you can say that the per capita demand for heat may change a little bit depending on the type of buildings, not too much, right? Depending on insulation and so on. But the underlying assumption we have here is that this is all for coal, right? Because in the orange variable, we have heat produced from coal boilers by population, unaccounted for. Mm-hmm. So what I'm saying is that if you use population, the whole population as a driver, we use the trend that basically represents all new coal boilers. What in the future, you may say that it's not all coal boilers for any addition of population, but just something to keep in mind. But you can see that if we use that heat demand by population for coal and accounted for in the energy balance, this is the only variable that changes dynamically. Mm-hmm. All the other ones, heat produced from cogeneration, from electricity boilers and so on, this is all government external decision, right? Mm-hmm. And for now, it's constant. So in the baseline, we will have to decide whether there is an increase or not in these variables as well. And ultimately, we need to check. What we could do is to check if there is a large increase in centralized heat generation, then we can assume that more houses, more buildings will be connected to that rather than having their own independent values. Mm-hmm. Right? So one option could be that we go back to what we said before, to generate total demand for heating. And then the amount of heat produced from coal boilers by population will be total demand minus all the centralized options. But what is left behind is coal demand from population. That could also be an option.
Not coal, but independent choice. I mean, I want to give them a choice.
Yeah. It could be independent as standalone in a building. Yes.
Is it share of population using centralized heating?
I'm not sure that you can use this variable.
No?
No, because if we say that the starting point for us is what the government says, like the cogeneration, electricity, and so on, these decisions are the ones that will determine how much heat is available from centralized systems. So what I would do, I will mention it quickly, then you can decide and implement it in case, is to calculate total heat demand by population, right? National heat demand, which is the same, right? Let's have it driven by population again. Mm-hmm. So this is the same calculation you have done before, but for the total, including the one that is not accounted in the energy balance. Of course, it has to include everything at this stage, right? So that we have a dynamic formulation for the total heat demand at national level. Then you take what is produced in a centralized way, so cogeneration, electricity, gas, crude oil, and determine, by doing the difference between the two, how much is the heat produced by independent producers or independent buildings. And from there, you can decide, again, out of what is independent, what is produced with what energy source. Make sense?
So, yeah, you're saying you're equating this one, I think all of this all of this apart from this whole, we don't have the data for what kind of, how much of the population use. Some of them use gas, some of them use electricity, which is like additional demand for electricity is driven by that. If we assume that this is the only one that cogeneration, this is the only one actually defined by government, that's not quite right as well. But I cannot distinguish the parts of how much is actually consumed by population and how much is consumed by public bodies here in these things like electricity and.
Yeah, so let's make it this way then. Keep it simple. If we lack this data, let's use what we have and just make assumptions about the quantities of one or the other. But when calibrating the scenarios, let's make sure to have a similar amount of energy, heat produced in all the scenarios, unless you change efficiency. Like if you change efficiency, it could be less. But otherwise, let's say that we have the total heat energy produced being the same. We just change the type of technologies that are being used. So that in one case, you can see more or less cost, more or less emissions, but ultimately you provide the same heat for everyone, which is exactly the same we do for electricity, right? You always match demand, but you can match demand using different technologies. So I would keep this the way it is now, actually, and even remove the heat demand by population accounted in energy balance, the latest additions we made on the right.
This one?
Yes, unless you want some of these variables to be driven by population. But we said it would be tricky, right?
Unless we just say that, okay, all apart from these ones, so this is the only part that can decide for themselves what they're using. Let's say this amount of population and heat can be changed according to, I don't know, market prices.
Yes. So let's do one thing, because we have many things to cover today.
Yeah.
Let's take a break now for 10 minutes. When we come back, we do a summary of and then finalize. Yeah, let's take a break, finalize this part, and then move on to the other topics afterwards.
Sure. Okay.
15 minutes, 10, 15, fine with me either way. Hello again. I'm ready to start anytime.
I'm here too. Let's see if the colleagues are back yet. Yes, Milan's here. Well, nobody else is, but yeah, okay, Estelle is here. Good. Ibek is here too. So we can continue then. So if there is something, colleagues, please do interrupt me with voice because I don't see the messages when I have the demonstration. So I thought of having a variable depending on the price per gigacalorie, or shall we use a different, or do you think something else is better? Here, additional demand for electricity is also partially based on the fact that electricity is the cheapest one, but it's not necessarily so, and it's not necessarily going to be so in the future. So shall we make that dependent on the price as well?
I think we need to make a decision on how to represent this. Do you want the model to estimate endogenously what energy source will be used based on prices, technology constraints, and so on? Or do you want to assume under different scenarios, a green and a business as usual, what the energy sources used will be?
Let's make it decide within the model. Based on prices.
Okay, then we need to have information on the cost of generation for all heat generation for all these technologies. Is that something we have?
For private households?
I think so, yes. As a starting point, yes.
We can assume so far something, but this can be found. We can find the prices for each type of energy for the population. And we do have the time.
Okay, so I would suggest that we first collect this data. We see, in fact, what is available. We see if the cost data are basically explaining the historical trend, right? If people, in fact, use the cheapest option or not. Maybe they use the most convenient, or they use the one that is subsidized because it's artificially cheaper.
Yeah, of course. They use electricity because it's so cheap. We have the spike, and we have 80% increase in winter month of electricity use, which is basically used for heating.
So I think once we have the data, then we can modify the model and start adding the price formulation. So what I suggest to do in that case is to calculate the price of one source, let's say electricity, relative to the price of the others. So that when one becomes cheaper compared to the others, then we can have the model indicate that there will be more demand for that specific source. But what I think will be difficult, and confirm on that, is whether we can add a stock and flow structure for the type of boilers installed in buildings. Do we have data on that, or not really?
Well, 2009, we have the data for 2009, yes.
Because one option we have is to model it like electricity with capacity and generation. If we don't have reliable data on capacity, then we can go straight to generation, which I think is what we discussed up to now. But I think it's clear. If we have, for the next time, I guess, for next week, if you're able to collect the data, we review the data together, and then we implement the changes, and we have the price impact determining demand. See one other aspect, if you can find that. If you can identify how much is in fact centralized generation as opposed to decentralized, meaning that how much is to be decided by households and house owners. Can you hear me now?
Yeah. I think this is why I put it in orange. I think this is the actual heat that the population can decide on.
Okay. So we know that the other ones can stay as they are because they're based on a centralized decision, and this is the only one that has flexibility based on prices.
At least for the most part, shall we say? Yes. Of course, some people use gas boilers, but most, I think, use either coal or electricity.
Okay, so then we will use the heat demand by population on accounted energy balance. That one we can keep. We add the prices. We add the calculation of, say, one price compared to the others. So what the degree of whether one energy source becomes cheaper over time with respect to the others. And this is what we use then to determine demand by energy source. So it will not only be coal. What are the other options available to households? I guess it's coal, it's gas, it's biomass or cogeneration also, electricity. So it's about the same sources available to households as we have in the centralized cases, right? So we will need to have, instead of just coal boiler or coal used for heat generation by population, we will need to have each of the technologies used by population. And maybe this would be a good way of start looking at the subscripts, right? Maybe we can work together to create a structure for population in this case that uses subscripts instead of the explicit variables for each technology.
Okay, so I'll look into these ones, the prices of all sources, and possibly maybe how many, I don't know. The latest additions to the building stock would have been anyway, I think, I cannot assume that. I would assume, I thought that they would be mostly multi-apartment buildings.
Yeah, and so likely not coal, I guess.
Yes, very likely not coal.
Okay. Yeah, if you can find something about that, we can start from the 2009 data, apply population growth, and determine what portion of the population uses what type of energy source. Meaning, if coal is being used only in old buildings and in none of the new ones, then we have information for calibration. We keep coal used somewhat constant or even declining over time. So just see what you can find, and next week we can start with this sector and this addition. Once we have fixed then the total production, because we have information on the energy used by source, then we connect these to energy consumption and emissions. It doesn't make sense to do it now if you have to make modifications next week anyway.
Okay. As for the other things here, do we connect anything to anything, or is it okay already glaciers? I think it's connected, right? Without electricity generation.
Right. On the demand side, yes. Is the production of electricity connected to power generation in the other sector or not? Because most of what we have here is the water volume and water flows. And then we have that variable at the center called electricity produced by large hydro. So here we are not estimating electricity produced by total hydro, just large hydro, right?
Yeah, but this is like 92% of everything.
So if we go to the power supply, power generation sketch.
I wanted to add renewables as well. Power generation? Or?
Yes. No, here is fine. So if you go to the electricity generation rate, that variable, and look at the table or the graph, it's at the center on the right, electricity generation rate. To the right?
This one.
Yeah, there, yes.
Do I look at the formula?
No, the table.
Is it? Yes.
Okay. So you see that in this case, you have hydropower large scale, right? How are these numbers comparing to the ones that you have in the other sketch that you're estimating? We need to make that comparison, because possibly we want to replace what we have here with the values that we have in your new calculation. So do two things to be able to see it properly. if you click on subscripts at the top right corner next to the control panel, let's remove all the other energy sources. And so you can select everything on the right side, selected elements, aside from the hydropower large scale.
Just leave hydropower large scale, right?
Yes, yes. Otherwise, you have too many numbers when we look at a table or a graph. Click again on large scale. Okay. Then call up in this sketch the variable that you calculate in the other one. So the total generation from large scale hydro.
How do I do that?
If you go to the previous sketch, see what is the variable name, then come back here and use the shadow variable to add it. Yeah, I don't remember the exact name of the variable.
Electricity produced by large hydro. Oh, what happened?
Yeah, it's a bit slow on my side. Okay, I can see the graph now. If you have the electricity produced by large hydro together in the same graph with electricity generation rate.
But wait, something happened with my electricity produced by large hydro. What has happened to this? Hit switch.
Yeah, it's 0 now, right?
Something's
off.
Something is wrong here. I didn't do anything, did I? 0?
Check the water flows. Check if there's something changing in the other areas.
It's fine.
Okay.
It's so weird. What's happening?
Click again on the production and see if, I guess the screen sharing is a bit slow on my side. So I guess there's a few seconds of lag between what you're saying and what I see on the screen. Right? So apologies if I say something that doesn't make sense.
Desired electricity generation. That's fine.
Click on the table and see if the value is in fact 0 or if there is a unit problem. No, it should be millions. The desired value is millions. Yeah.
And here, this is not millions, but
thousands instead of millions. But if you multiply by 1,000, then the value is about right, it seems. So we need to see why.
Because I divided by 1,000 here. Why is that? Because no, probably this is because actually I was rebuilding the model from the previous one because I was trying to import some of your sketches of Kazakh side.
Okay.
And I had an error which was persistent. I could not actually import them. So I started from scratch again.
Yeah, okay.
So yes. It's scary.
Okay, so let's go to the other sketch and compare if the amounts are similar or different. Yeah, they're not the right variables, right? You have the effect of water scarcity and then the electricity produced by large hydro. Yes.
Electricity generation rate?
Yes, and your electricity produced by large hydro. Yes, these two. Okay.
They look similar.
Yeah, so they're already fairly, historically, they follow the same trends. Good, so the calibration is fine. And then we already had embedded a growth in the model before, probably because of the growth of demand. Hydro was one of the options chosen as remaining with a large percentage of supply. But the fact that they're consistent tells us that we can probably just replace one with the other. So a question for you, how would you do this? Where do you think is the right place for substituting the calculation we have in the model in this sketch for large hydropower with the ones that you did as brand new? So what is the right value when you can substitute one for the other? If you look at the model, where would that be?
Let me just see. Power generation capacity. This is a bit too big already here for some reason. We don't have 5 gigawatts. We have 4, well, almost 4. At that time, we had 3.
That's probably because of an inconsistency in the load factor, that maybe it's not high enough or not as high as what you use in the other sketch. So there is an artificial increase in capacity to make generation match. But with what we're generating in the other model, we already have power generation capacity there, right? So this would be a bit of an overlap. This shows capacity under construction for hydropower large scale, meaning that you see from 2020 or shortly after, you want to add more capacity. But this is done on an annual basis. What you have in the other sketch is a large project being introduced. So it's probably a better formulation what you have in the other sketch, because hydro is not added every year. You have a large project, it's done, and then you have another project and it's done. So this should be bypassed in this case, right? We should not use this one. One option would be to replace directly the electricity generation rate and say this generation rate.
Can we make a switch? I don't want to delete it.
Yes, of course. You can make it a switch for endogenous or more detailed large hydropower generation.
Would it be to endogenous? This sketch is endogenous.
Well, they're both endogenous in a way, but one is just more detailed with the water flow.
Shall I call it then? Switch to large hydro generation, depending on, and this would be gold and orange. So this is not the policy, but this is a switch. So it would be orange. And then how do we connect it further? Here, do we change this formulation, electricity generation rate?
Yes, I think that is the one that we can change directly. But when you open it, you will see that subscripts are being used there.
Oh.
So we need to make a few more changes.
Okay. We need to do that for each equation, right? So we add if, then else, right?
Well, see this one. No, wait. Under subscript, just above from where you are, you see this is fossil fuel and nuclear. So we are not doing anything for fossil fuel and nuclear, right? So this one we don't need to change. Yeah, go to the next ones. So if you see where you have fossil, open it again. Yeah. So here you have where you are now. You have 1 and 2. This is other renewables than hydro. So it doesn't include hydro. This one, right? Mm-hmm. If you go to the third one, this is hydropower, you see? So it's basically summing up together. What it's doing, it takes the minimum value between the power generation capacity multiplied by the load factor, hours per year effect of water scarcity on hydropower generation, and the desired electricity generation for hydropower. So it's the minimum between what you can produce and what you want to produce, right? Mm-hmm. So what you can do here is you can decide to use a switch, potentially, between so if the switch is 0, use the equation you already have. Otherwise, if the switch is 1, use the new calculation you made in the other set. And that would make so that you cover both. One aspect to consider is that here we look at both large and small hydropower, so the sum of the two. But with the formulation you're adding now in the other sketch, we only have large hydro. So let's see how it works now. And then in case we determine whether we need to add small hydro specifically as an extra variable.
Now we set it to 0. Shall we go here? Then it looks really weird. Do we leave it calculating each month?
I think so. Each month, yes. Otherwise, we don't capture the seasonality you have in the other sketch, right? Mm. So if in this case, it's difficult. Look at electricity generation, not the total amount first, because total electricity generation takes into account the other sources, right? So in this case, you only have hydropower, right? Hydropower large scale, and we see that they're matching in the two scenarios, when the switch is off and when the switch is on. Mm-hmm. There is a lot more oscillation in one case than the other case. Like if you go to 0 now, you have them at the same level. So when it is 0, what are we taking as the input? We are taking the original one, right? So the first thing we see is that there is a lot of oscillation because of water scarcity that we had done before with the climate data and the threshold. When you turn the switch to 1, there is a lot less oscillation because we have the glacier in this case that serves as a buffer. And so we have a lot less of that. So I would do another thing here to make it more visible. Stop synthesizing, because we see that the switch now works, and run a new simulation. So you have the one we have now, which is endogenous, run another one with the switch on, so that then we can look at the full graphs, we can look at the full tables and so on, and compare more directly. Okay.
I deleted too much accidentally. Control panel. Large hydro. Why is it not showing? Large hydro is red. Ah, maybe they're the same. So probably the blue and...
Yes, right now this this looks like the one you have generated with the glaciers, right? Because it's constant in the future. Yeah, so it looks like they're all the same. So rerun the one with just large hydro, not on, and set the switch to 0, and then it should look different. So probably you have two simulations running with the same assumptions.
Yes, maybe it's the same one.
Okay.
Did they change something?
Try and rerun the model.
Ah, wait, I have to change. Wait, I have to...
The switch to 0. Okay, now we see the differences, right? So the first difference is that we see a lot more declines, seasonal declines in the original simulation that we don't have in the other one, right, in the blue one. Okay, and then the other change is the longer term difference, meaning that after 2050 we have a continuous increase driven by growing population in one scenario, and then it's constant in the blue line because we are not assuming any larger expansion, right?
We can. I mean,
of course, we could.
We can, yeah.
So this is what we have now, and it helps reviewing it for calibration and say, okay, so it seems like we have a shortage. We would have more demand from hydropower, but in the blue line, we don't capture that. So let's see what happens in the model when hydropower is capped in this case. Let's look at the other variables, like the share of renewables or something that gives us an idea, share of renewable generation. You see that it was higher before and it's less now because there is something else that is making up for that difference, right? Now let's close this one and let's look at total generation, just to see if total generation is the same, if you're matching demand or not.
It's more.
The total electricity generation now is higher. So let's try and figure out why that is the case. It's unusual that it's higher already historically, right? It could be higher in the future if you use different technologies, but somehow it's higher historically as well. It looks like it's almost twice as much, right? Like if hydropower is counted twice. So let's try and review that and figure out what is happening. So if you close the graph, we look at the equation for total electricity generation. Yeah. So this is just the sum of electricity generation for all power generation technology. And these are the power generation technologies. So there may be something off when we have hydropower, large scale and small scale. So let's confirm here and check what happens for all the subscripts. Now we select all the subscripts because we want to see what happens with the other technologies. I close this one. You select them when you go to the subscript tool right on the right side of the control panel. Yes. So here you can select all of them. Okay. And then open the electricity generation rate variable with the table, because this is the one that is being summed up to have an impact on total electricity generation, to estimate total electricity generation.
Large ones,
okay.
Yeah. This is
you see, large and small are the same. So this is an issue we need to pay attention to when we work with subscripts, right? Because we have to be careful not to double count. So let's go again into the equation for the generation and the hydropower equation, not the total one, just the electricity generation rate. Yeah. The third one, yes. This is hydropower. Now, there's something you haven't seen this, so it's difficult for you to realize. But if you click on range, when you have subscripts just below where you are in range, you have here what is included in all the subscripts that you have. So here you have the detail and all the elements. But if you click on range again at the top in this drop-down menu, you can see that there are aggregations of these substrates, like all but steam coal. It's all other sources, or all other technology that are not steam coal. All renewables is the sum, or lumping, or considering only those that are renewables. Click on hydropower here. Well, you see, if you click on it, it goes up to, so the equation. But we need to figure out what is in hydropower. So if you close this one and click again on the subscript control panel or subscript tool. At the top, you see you have sub-ranges, right? When you have all, none, all but steam, coal, all renewables, scroll down to find hydropower. And there you see that hydropower includes large scale and small scale. Okay, so whenever we work with the subscript hydropower, we are changing both of them. Okay, at the moment, what we have in the model is that we have power generation capacity for one and the other. And so generation was fine because it takes into account the fact that you have a certain capacity for one and one for other. But if we go into the electricity generation rate equation that uses hydropower, that is the sum of the two, and we say for both of them, we use the new hydropower generation value, then we apply the same generation that we have for the large to the small ones as well, okay? So what we need to do here is the following. And again, this is not, it's not something you know, but you could not have known this before. So instead of the subscript hydropower at the top here, we need to introduce the subscript large hydropower. Yeah, it's okay to do it. So this one could be either large or small hydropower. You can decide because we need them both. You have to be careful and use the exact same words that are used for the subscript. So when you have range in the subscripts, click on the drop-down menu, select power generation technology. Okay, and see this is hydropower large scale or hydropower small scale. You can click on the name in the list of subscripts, and it just transfers it there directly. Yeah. Okay. So this is the large scale. So if you go back to equation 3, okay, this one has to be hydropower. Yeah. First, start with the subscript. This has to be the other type, right? This has to be the small scale. So what equation do we use if we stay here for small scale? We can remove the if then else because we're not dealing with that, right? So all the first part, the if then else up to the minimum function can go away. Right? Actually, do one thing. Sorry, just copy all of it because we'll need it for the next one. Sorry, it just makes sense to do it.
I think I did already copy it.
Okay, then paste into the 4 in case, yes.
No, I did not.
Well, we add the if then else later on. It's okay. So let's go back to the 3. So we fix that one first. So here we start with the minimum between power generation capacity, not hydropower, but only hydropower small scale. Then load factor, hydropower small scale. And then hours per year is the same. The effect is the same. Desired electricity generation by technology, hydropower small scale. So this one is fully done for small scale only. Let's go now to equation 4, where we can add in the if then else with the switch. And then we use these subscripts for large hydropower, or when we have to switch, we don't have subscripts anymore. So if the switch large hydro equals 0, let's use the original equation. Minimum power generation capacity. Yeah, you can do that first. Yes, it's okay. Either way, it's fine. So this is large scale in the subscript. Load factor, large scale. Perfect. And then these are electricity generation, large scale. And then comma on false, we have our own electricity produced by large hydro. Yes. Okay. Check the syntax. Press OK if there is no mistake. Now let's rerun the model. Change the simulation name. So this is a new version 2, let's say. Both with the switch off and then with the switch on, so that we can compare with what we had before to see if it's consistent, and then we can reassess if the switch is working fine. Okay.
Oh, only for 16 variables shown on the graph.
Yes, because we added a subscript and we have 2 more scenarios, and Vincent cannot load more than, I think, 16 or so scenarios at once. Yeah, remove everything that is not hydropower.
Small scale, I'll leave it here, or?
Yeah, you can add small scale, but it should be 0 or very, very small anyway, or close to 0. Yes. I click on this graph. Yeah, so we see the numbers are reasonable, meaning we recognize them. The blue one is the electricity generation rate, large scale. okay, with the switch on, which makes sense because it's the capacity, it's the generation we have from the other sketch. So it shows up when the switch is on. The red one is the one with the switch off. So the fully endogenous formulation, which tends to grow again in the longer term. And then the green one was the previous one with the switch on. I'm not 100% sure why there is a difference between the blue and the green, but it's easy to compare. We can figure out which one was right. And then we have the other ones now, the small scale, that if you click on the table, I think the small scale now is either set to 0 or very, very low. But that's something we can improve with calibration. Yeah, it's set to 0. If you continue scroll to the right, 2018 or 2019, I'm not sure we had data when we did the model first on small and large, so it's all accounted for in large production, which explains a bit the difference we have between the simulations in the other sketch and the earlier simulations. So it seems to work at this stage. Go check the graph for the total power generation, the one that sums up all the energy sources, to see if we still have a much higher value or if it's more consistent.
Oh, no,
Okay.
we have a better one.
So the blue one now is a lot more aligned, right, with what we had before. We could compare now demand and supply, so total electricity demand in the same graph with total electricity generation. But before you do that, you can remove the old scenarios, otherwise the graph is a bit too messy. So if you go to the control panel, yeah, the standard, yes.
The last one, right?
The last, yeah, the third and fourth one, yes. Okay, perfect. Now you could put together in the same graph this total electricity generation and the demand for power generation, desired electricity generation on the top left corner, towards the top left corner. Okay, yeah, they're very close, you see. And we have a little bit more of extra generation now in when we introduce the big project, right, in the medium term. But otherwise, yes, it's fine. The other thing we see is the total electricity generation. If you click again on that variable and see the graph, just want to verify. Yes, so now the total generation in the blue line stays somewhat constant. So what we're doing by using that generation is that we're forcing down the generation from hydro, which is not replaced by other technology, by other options. So as you said before, when we run the model, we need to introduce new projects so that we match the potential growth in demand. It could be done endogenously, or it could be done as a scenario assumption.
We can introduce some small hydro because within the policy here, well, the policy that we are now sort of developing, we are going to have about 200 megawatt of capacity within the next 3 years, 2% of which are going to be small hydro. This is like with feed-in tariffs, so they should be pretty fast, well, built pretty fast, for about 200 megawatts for sure. And then depending on how the energy system will cope with that, because this is higher prices and stuff, they will, introduce further quotas for that. But actually, you can build without any quotas, just for the price of electricity that you have now. Also small, well, anything, but don't count on any feed-in tariffs or anything.
Okay, so let's close this graph and see before we take a break. What can be done here if you want to run alternative scenarios. So if the switch is 0, so we use the original model formulation, on the left side, you see 2 orange variables, right? 3 actually. We have the policy switch renewable energy and the electricity generation shares green economy scenario. So when we don't use the large hydro generation in the other sector, the policy instrument here is to determine what is the share of generation by technology. On the other hand, the other thing that we can do, especially when we have the large hydro switch on, is to manually introduce new projects, both for large hydro and small hydro. So we can change the way we modify the policy, so that if you say we have these many megawatts that will be introduced, we know it, we are somewhat certain, there are permits being given and so on. Then instead of determining the share, we can actually introduce in the model exactly the amount of megawatts that you expect will be built, right? So this is just to say that we can decide what type of policy input we use in the model, depending on the type of information you have. So to me, when it comes to power generation, we are basically ready to run new simulations for the policy briefs, right? We could say, what if we include the potential generation from large hydropower? What if we change assumptions on precipitation? What if we change assumptions on temperature and warming for glaciers melting and water supply? What if we simulate additional small hydro as opposed to large hydro or other technologies? So in this sector, I think we have quite a bit that we can mention, in connection also with the distribution lines that we have already worked on, because different technologies will require different efforts for distribution as well.
But they are not described here. We are not describing the effect of small hydro or solar on distribution lines here.
No, but we will have to do it manually, right? We will have to say, if you have a large hydropower project and you have to rely on long distance distribution lines, what happens if you were to invest in improving efficiency? What happens if you were to invest in modernizing, retrofitting the distribution lines? You would say we have less losses, and as a result, we may need less investment in additional capacity in the future, right? So you can see that one investment in distribution lines avoids another investment in power generation capacity. So that is the type of assessment I would do. In a way, why invest in more capacity if you're utilizing it in a suboptimal way? Right? That would be the underlying question.
But shouldn't we have all the variables in before we do the policy analysis?
I would say that we should try and run, maybe not this week, but next week, let's say, when we have refined them a bit more. We can start running a policy scenario, and out of the results we get, then we realize exactly what is missing and what needs to be improved. In my experience, I get a lot of ideas when I start running the policy scenario, because I have an expectation on what the outcomes may be. And so if I run the model and say, I introduce new hydro and I have more power losses, that doesn't make a lot of sense to me. Then at that point, when I see that number, that graph, I would say transmission lines. Why don't we improve efficiency for transmission lines? And then if we have information on the cost, I would start comparing the cost of expanding capacity with the cost of improving transmission lines. And so it's by simulating the policy case that I get the better ideas to complete the analysis. Beforehand, it's very difficult to have everything in mind and everything clear to say, okay, now we have everything we need, let's go ahead and run the policy case. Just a final comment before we take the break. This is, I see it as a peculiarity of the modeling approach that you use. When I work with energy modelers, let's say that use the Times model or Markal model, that takes hours to run. They want to have everything fixed before they start running the model. Because if the model is not ready or done properly, they waste hours, right? They wait for the results and they say, oh no, the results are not what I expected. I forgot to change this or that. So they want to have everything done perfectly before they run the model. In our case, the simulation takes a second or two. So we have the luxury of running a lot more simulations and learn from the results of the model to improve the next simulation. So don't be afraid of testing the model and running new scenarios. It's perfectly fine. It actually helps understanding what's going on and what to improve.
Oh, good. It takes a bit of pressure because it's not ready. How are we going to run it? I don't have all the variables.
Yeah, in some parts will never be fully ready, right? In some cases, you may want to do something, but you cannot find the data. So instead of running around looking for data for a day or two, or maybe a week or 2 weeks, run the model. Test what happens if you use a small number or a large number for the data you're missing. And see if the results don't change much, then you're better off by doing sensitivity analysis that is quick. If the results change a lot, then okay, I really need to find this. I have a confirmation now. I have to look more for this type of data. So let the model help you in the process. You see, it's a lot more time effective.
Mm-hmm.
Okay. So then I propose that we take another 15-minute break. And then when we come back, unless there are other changes to review for energy, as Hassel was suggesting and discussed also yesterday, let's look into the other sectors, agriculture, possibly tourism, the other areas, Tatiana, where you have done some work or where you plan to do some work, with, in this case, an eye on the policies, right? So now we said we need to improve the model to make it more comprehensive, and the policy comes at the end of the process, where you would say we're not ready because we missed some indicators. Let's try and use the opposite entry point. When we look at the other sectors now from scratch, let's say what policy may be relevant to run. And based on what we want to run, let's see if there are more changes to be made and more data to be found. Okay, it's just a slightly different approach, but the tasks are the same.
Yeah, because besides, I mean, I was trying to look for even the definition, I'm sorry, of sustainable agriculture. This is like...
Okay, I'm back. Apologies for the delay.
That's okay. So I'm here at the agricultural land use. So shall we start with the land use as aggregate or no?
So what are we doing now? You want to show changes you've made, changes you want to make, or are we trying to identify intervention options to test?
Let's try, well, I wanted to discuss a bit what we had in mind for agriculture. We did add sustainable in addition to organic, which is now I'm not sure whether it's a good idea because I cannot define, well, there are at least several factors that we have to take into account. Let's say, okay, organic is easier defined because there are some standards. So you know genetically modified organism, and this is actually defined in the program. So no GMO, no pesticides, no mineral fertilizers, no artificial additives, no or minimum till. So we have like 5 things that are prohibited. For sustainable, I cannot say that we prohibit any of these things as such, because it depends very much on what you're growing and what are the conditions. And sustainable agriculture is pretty much oriented towards providing all we need to have in food and fiber while preserving all we have, And for that, I don't think this is a crime to use mineral fertilizer. Absolutely not. I don't know. Pesticides, they can be different ones, artificial additives, okay, maybe not. But then again, minimum or no till, this is not a panacea, and it can only be used for several cultures, not for everything. So I don't know how we did this small change, but I did not go further because I had this further definition problem. And besides, if we add this...
How detailed do you think the analysis has to be useful at this stage? Do you think you have to look at, for instance, the impacts of each of the actions that you have just mentioned? Or is it okay to lump together the different types of interventions and to say, if we take this as a package, organic as opposed to sustainable, let's see what the impacts are for sustainability. And we need to define what sustainability is.
As a package, but then we have traditional, and we don't have the data for, let's say, improved or decreased yields for such matter. We're not in Africa again where the yields can improve when you use organic agriculture. They might decrease, and we don't have data for that as well.
But what if you do a sensitivity analysis and we say, what if they decline by 10 or 20%? What if they increase by 10 or 20%? And we can use some reference studies from other places in case. Just as a
the point of introducing organic and sustainable, there are several things that I would want to connect it with. Organic, basically, this is of course connected to our tourism and to GDP, obviously, because we are supposed to sell it at higher prices, and sustainable as well, and to less soil erosion, more efficient water use. So to more effective use of resources, at least sustainable one. I don't know, organic is a totally different one.
No, but so what is the policy story you would want to tell? I guess from my side, correct me if I'm wrong, would be to say, if we switch to more sustainable, say different degrees of sustainability, we can figure out what that means. But the sense of direction is the same. If we switch to something that is more sustainable from an environmental point of view, then we may have potentially a reduction in revenues for the sector. In the worst case scenario, yields decline. On the other hand, if there is access to premium prices because of international markets or upscale domestic markets, that could be somewhat offset or fully offset to be verified with the model. Then in addition to that, we have some other factors to consider. One is that there could be a positive impact from tourism. It's tangible, but not for the same actors, not for the farmers, right, for others. Then there are some costs that could be avoided. The cost of soil erosion, water pollution, health impacts, and so on. That can be quantified. I guess we can quantify them, but they are normally externalities. They're not really considered by anybody. It's just something we have to deal with, right, depending on who's affected. So overall, you can say we have to test if it makes sense to give up something on the farming side, meaning that revenues could be lower, if we obtain more than what is lost in other areas. Let's see what are the conditions to make this happen. So that we could say with the model, if we look at an analysis, we run a sustainable or organic scenario. We see by how much the yield might decline. And then we say...
One question, are you making sustainable and organic equal again? Or?
No, it could be one or the other, but the type of analysis is the same. So let's just talk about organic for simplicity. So let's say we do organic agriculture and it turns out yields are 10% lower, okay? Then we will need to say we reach the same economic viability as before if we have a premium price of, let's say, 15 or 20%, right? So with the model, we can calculate what that has to be. Why a 10% decline in yield is compensated by, let's say, a 20% increase in price? Because it may well be that organic carries higher costs. So on the one hand, you have to pay more to adopt these practices, be certified. And on the other hand, you have less revenues. So in my simplified assumption now, 10% is lost for revenues and 10% is the extra cost. So we can say, unless you have at least a 20% premium price, this is not going to be economically viable for farmers. But then, if we add the other benefits, the benefits to tourism, the benefits to water quality, health, and so on, so avoided water purification or these type of things, then we can see that the societal value is possibly higher in any case when we use organic farming, despite the potential reduction in income for farmers. So this gives a very clear message to the government, I believe. First, that from a societal point of view, it is worth doing. Second, is that if they want to realize these societal benefits, they have to convince the farmers. And the farmer will not switch to organic if they know that they will lose money, right? So what the government can do is either support the creation of a market, support the creation of a labeling system where there will be a higher probability for a premium price being established, or it could provide incentives in the range of these 20% of revenue that otherwise would be lost, or profitability that would be lost, to make so that farmers do not have any short-term negative impacts. If anything, they will have a positive impact when they produce and sell with the premium price. So that is sort of the policy argument I would make. It may not be the right one. Of course, you can change it in whatever way you want, but I wanted to mention it from my side first, because this has to be sort of the statement or the storyline that guides how we modify the model and how we set up the model for the different scenarios. Okay, so first identify the story, and then we look into the model and say, okay, what do we have? We missed this, or we have that. We have more detail in this area, less in the other area. What does it take to realize that storyline? Okay, you see what the process is?
Yes. Yeah, let's do that.
Okay, so first, exchange internally, you and colleagues, on what is the most powerful policy message that you can generate. And once we have that agreement, then we start looking into the model about the options. And you see now, organic or sustainable is more of a secondary discussion because the analysis will be the same for both. I guess we'll just go for the one that gives us more certainty in terms of parameters and inputs.
But the results will be different.
The results will be different, yes. I mean, the cost of implementation will be different. The potential for the premium price will be different. So the numbers will change, certainly. But the type of approach we use to carry out the analysis may well be the same, right? We may end up using the same indicators to evaluate both scenarios.
What I would want to show, for example, is that we do have to look into the soil quality and water use, that in case, well, at least for those two, and pastures as well, that unless we do save them, then in the future, in the very near future, we will not have the same yields, or we will not have the food security will decline. So this is something I like to scare people. So I would prefer to say, okay, guys, if we don't do anything about this, then the deterioration will reach the extent after which it's going to be, it's going to be more costly to actually make amends than do something about it now. This is what I want to say, I think.
So the economics would come in as, by the way, it also makes economic sense in terms of the analysis.
For me, economics is like, it's common sense. Economics is not only 3 years, it's not 5 years, it's 50 years as well. So yeah.
Right, but if the entry point, what I meant is that if the entry point is food security, you would save, in a way, you try to scare them on a personal level, right? But then you would say, it also makes economic sense to do it this way, right? In addition to solving a problem that you may have on the food availability side. So it comes as in a way, as a no-brainer. It should definitely be done if you can address both concerns.
Yeah, I think, and if the primary, you would actually say, if we use the economic considerations as primary, you would say, oh, this is more profitable, but this is not at the moment. Because...
But it may not be profitable. What I mentioned earlier is it may not be profitable for some economic actors, but from a system point of view, maybe it is. Right? That is also what we want to highlight. But go ahead. I'll be more silent now and follow your discussions and the way you want to frame this, so that then I can help more on the modeling side.
Shall I then go into the Russian channel or something? Let me see. Yes, I'm going to Russian channel to discuss it. Коллеги, меня слышно?
Yes, I can hear you. Yes.
You can hear me in Russian as well.
Да, слышу.
So, I mean, since we all speak English, let's maybe speak English. So what do you think? I mean, which approach shall we take? То есть нам лучше как с экономической точки зрения посмотреть. То есть у меня в задании есть такое, то есть посмотреть, что будет лучше. То есть мы смотрим разные policy и смотрим, какой будет наибольший эффект на ВВП и employment. То есть это в моем задании для GIZ. Но
да, будет интересно.
Именно с экономической мы не будем, как бы вы не считаете, что лучше смотреть в первую очередь с точки зрения food security?
Ну, мы хотели бы пилотные, вот как раз с учетом этих критериев определить, чтобы дальше продвигать для нашего проекта, в принципе. Потому что в сельском хозяйстве, food security, но для фермеров в конечном итоге это важно увеличение доходов и обеспечение занятости. Это в реальной практике, как вы знаете, в рамках наших ЦДС, да?
Нет, я знаю, но вопрос в том, что правительство должно будет выбрать политику. И для правительства, мне кажется, благосостояние фермеров, я не знаю, насколько оно их заботит.
Конечно, заботит. Это борьба с бедностью и так далее.
Хорошо.
Социальное развитие.
Да. Мне кажется, когда мы начинаем говорить о потере безопасности, о безопасности, в том числе продовольственной, либо энергетической, это как-то их больше затрагивает.
Нет, это я не умиляю важность вот этой части тоже, как бы, продовольственной безопасности, да, но вот с точки зрения нас было бы интересно посмотреть, какие интервенции мы можем дальше продвигать с точки зрения доходности и занятости.
Учитывая, что у нас более 70%, да.
Когда мы пойдем это все валидировать с частным сектором, мы же ожидаем потом дальше пойти это все обсуждать с бизнес-ассоциациями, насколько это будет, да?
То есть вы хотите смотреть не на ВВП, а на доходность именно фермеров?
Нет, и это же также включается, потом отражается в ВВП, да?
Оно отражается.
Доходность, да, доходность, занятость и ВВП, естественно, потребление.
Айбек, вы что-то начали говорить?
Да, я хотел сказать, что с точки зрения продовольственной безопасности у нас получается практически 70-80% импорта. Просто, о какой продовольственной безопасности говорить?
Может быть, мы начнем с малого.
А потом с точки зрения социальной стабильности.
Наших заданий, да, что уже как бы определено и согласовано. но в дальнейшем мы можем взять и другие.
Не, я поняла,
интервенции,
Асель, я вас поняла. Если Айбек, вы хотите что-то добавить, тогда давайте добавляйте, мы вас слушаем.
Ну, у Айбека то же самое, доходность и занятость.
Нет, я знаю.
Я
просто
думаю, с точки зрения социальной безопасности, стабильности, будет лучше говорить о доходности и о занятости, чем о продовольственной безопасности.
Можно Эрмека
Да.
еще услышать? Эрмек, вы можете говорить? Окей, ну понятно. Мини-опрос тогда завершаем. Будем смотреть на занятость и доходность сельскохозяйственного сектора. Эрмек, ага, не может пока разговаривать. Хорошо, ладно, тогда я пошла обратно в английский канал и будем смотреть с точки зрения доходности и занятости.
Пока вы не
Okay, so the
ушли.
people have spoken.
Не ушли уже.
They don't want to scare anybody with food security because it's already scary enough. And they all four looking at the increase of income and employment in agricultural sector because it's like 66% of population, which makes sense, obviously.
Okay, so let's see what indicators we have in the model already that can help us tell the story. So income, I think we have because you have job creation from both conventional and sustainable agriculture, sustainable/organic. We may need to identify exactly what you have here on the left side, the blue variable, additional employment from sustainable or organic agriculture, right, for both, if there is higher labor intensity or not. In my experience, this is about 10% more labor intensive, but the more local information we find, the better. Then from employment, we estimate income, higher labor intensive. Then what we calculate in addition from employment and say the average salary for those that are employed could be GDP or revenues per farmer or per person employed in the agricultural sector, which includes the profits basically from either self-employed people or medium to large farming activities. So we have these two indicators. Now, of course, employment depends on land use and on labor intensity per hectare, and revenues and GDP depend on land, productivity of land, which also has to change when we do different types of land management practices, and the market price, which also changes, as we said.
Mm-hmm.
So we have all these elements that sort of converge into the GDP and the income calculation. Is there something else you may want to add to make this more aligned with your view and vision, or the indicators are enough? We actually have the ones we need.
Well, from what you say, we seem to have everything, so.
We will need to check the parameters, right? The key parameters is the additional labor intensity, additional value added or premium price, change in the yield of land productivity. So these are the factors we may need to check in more detail.
We have additional value added 10%, additional employment 10%.
Just very simple for now, yes.
We, agricultural land, let me see if we have something. We did not add, I think, the degradation of agricultural land, soil degradation. Or do we have it somewhere?
No, I don't think so. I did show the example for the Kazakhstan case, I believe, but we don't have it here. If you go to the production, then we can see what are the factors that affect the land productivity. So this is where we have the land, stocks and flows, traditional, sustainable, and organic, right? The three, remember we worked on this together. And then out of the land that we have here, we have the production estimate. So this is only where we have the land. Then if you look at the list of sectors or sketches, or we can use the tree diagrams as well. If you go to crop production, okay, yeah, you see at the top, we have the current yield per hectare that is then multiplied by land, types of land. So here at the moment we have, go up just a little bit. Okay, we have the average yield per hectare by crop, which is a time series, just above the current yield per hectare. Then we have a policy switch that can introduce an increased productivity effect. And then we take an extra impact for the sustainable or organic values. You see that at the top, we have a soil degradation index, we have an impact of fertilizer use on agriculture yields. They are not directly connected now, but these could be connected to show that when we stop using fertilizers, chemical fertilizers, there could be a temporary reduction in productivity. Or at the same time, as soon as we start using organic fertilizers, there would be a positive impact. And then we have this soil degradation index, in this case, that, remember, was calculated for livestock, not for crops.
Mm-hmm.
All right. So in case, if you want to connect it and show that the current yield per hectare may not be constant, or in fact may be declining because of soil degradation, then we may want to add an extra sector just for that. Click on the current yield per hectare and look at the graph to see what is the current expectation in the model. So you see now there is, we have to see whether this is already the green economy case. Yes, it is the green economy case. So there is an expected increase between 2020 and 2040, and then constant. What we can do is that we can turn off the green economy case. I think there is that policy switch just above. This is dependent on the G policy switch. So we need to turn the G policy switch to 0. You can call it up as a shadow variable here as well if you need it. It's faster. And normally I would go to the interface at the top and run the scenarios from there. But if you're working within a sector, just call it up and use it here. Okay. So if you set this one to 0 and then change the simulation name, call it BAU rather than G.
Okay, this was the simulation. Let's just call it. And we run it, and then we set it to 0. No.
Okay, so this shows that in the business as usual scenario, we are not expecting any change after 2019, right? Constant. So if we add soil erosion, we will see already that it will be a decline in the medium and longer term. I don't know how big, but likely a decline that could be countered potentially by the use of more sustainable or organic practices that reduce soil loss and erosion. So in a way, what we are doing now is, just for you to understand the process, we have identified the policy storyline, right? We have identified that we have the right indicators. Now we are looking into how these indicators are being calculated to see if there are modifications, additions to make to properly represent the positive impact of more environmentally sustainable interventions, like avoiding the use of fertilizers so that we avoid soil loss. So we want to make sure the model can produce the right results for the right reasons, meaning the right dynamics are embedded in the model.
Yeah, I understand, but this is the soil erosion is not really caused by fertilizers. It's caused by watering practices and stuff.
Mm-hmm. So we could do that. Yes, we could represent it more explicit in that way then, if we have the data. Yes.
And then we did want to add the runoff of the fertilizers. They have a runoff, and they will have the water pollution connection there. Mm-hmm. So these two, maybe you have it? Or
we'll check. Go to fertilizer use, to the sketch, and we can use the 3 diagrams to understand where this is being used.
Fertilizer use in this one?
Yes.
We had this one. This is on yields.
Yes, that relative mineral fertilizer application for traditional, where is that coming from? How can you find where this is calculated?
This I know this is from here.
Right, you can either go directly to the sector, or you can also select it and to do edit find or edit find again. Yes, so here we have the application of fertilizer, right, that we worked on together. Click on any of the relative values or the absolute value, chemical fertilizer application for organic, and then select the, not the equation, select the uses tree to see whether it's being used somewhere else.
No, not yet, it's not connected.
Okay, not this one. What about the absolute value, not the relative one? Okay, also only used for the relative value. So these are not connected anywhere yet.
Apart from this one. And this goes to soil erosion index. Actually, Initial chemical fertilizer application for soil erosion index.
So go check the sketch, the sector that is called soil quality, or I think we have one, and I'm opening the model on my side as well.
Soil degradation.
Soil degradation, yes.
Oh, we do have.
Right. So you see here we had some chemical fertilizer, you have some pesticide use, livestock density, nitrogen from manure, all affecting that soil degradation index.
Shouldn't there be two soil degradation indexes, or because this pasture is a bit different? I mean, it's influenced by different factors. You don't water pasture, you don't put fertilizers on pasture.
Yeah, no, it could be, in this case, I guess it's aggregated because if there is a problem on soil, if you look at the potential problem of water pollution, there is a sort of a confluence into water. And so whether that is agriculture or pasture, potential pollution and soil will flow into a river or so. But perfectly fine to disaggregate, of course, especially if you want to single out the impact on crops only, and then the impacts on pasture land only, and then sum them up to look at the aggregate environmental and social impacts. Yes.
Or we could have like a share of pasture. We could have total agricultural lands and have a share of pasture, and then we can have the effects of pastures on this share. Or is it better to have a separate one, like
if they're different causes, I would keep them separate and then maybe aggregate them afterwards, but start with a different value. I mean, if you say watering is one of the key causes and we don't have it represented here and only applies to crops, then worth having it separate with that impact added as well.
So then do we add it here, the soil degradation index for crops? We can rename that one, can we? Pasture?
Either rename it or create a copy and just remove the livestock components, as you like. See first whether the relative value or the soil degradation index is used somewhere, or this is just an output indicator.
Relative natural capital, total productivity, ecotourism.
Yeah. So this is now looked at as total pollution, basically, right? As total environmental damage. So up to you. If you want to use one for crops only, I would say create a parallel one so that you're not affecting what happens in the other parts of the model for now.
And then this is influenced by we have in watering practices. Do we have watering here?
We have an agricultural water demand sector, right?
Cultural water demand here. And here we have rain-fed, system efficiency.
So we have on the left side water demand by crop, which is then multiplied by the types of crops we have to have total demand. We subtract precipitation to see what is the net additional water requirement that is not supplied by rainfall. And then we look at the irrigation or watering options that we have with a specific efficiency for each, so that we can look at the potential efficiency of, say, flood agriculture, center pivot, or drip irrigation options.
Can we? This is not here now.
Well, not there, but we could do that, right? We have a policy irrigation efficiency table. So we could approximate with the policy inputs the use of one or the other technology, depending on the efficiency we assume. Like center pivot is around 40%. I think this is what we have now as the policy irrigation efficiency for the green economy scenario. Drip irrigation goes up to 80%. And we have the baseline now as being 27.5% for the current baseline irrigation efficiency. And then water efficiency for canals, which is 0.7, assuming a 30% loss in the system just for conveying water. But so by changing these parameters, we can approximate the use of different irrigation options.
But this does not have an effect on soil degradation. This just deals with water efficiency. I mean,
exactly. So how is the water affecting soil degradation and soil loss?
We can separate it for different kinds of irrigation. So drip irrigation, basically, it's great. I mean, we don't have soil erosion, and it's just the flood irrigation, which is mainly now.
So what could we use for the variables we have here. We have water conveyance, which basically means that if the efficiency of water conveyance is low, you have more water lost in the system. That becomes runoff, right? And so it's not positive. At the same time, we have the irrigation efficiency, meaning that if you have 80% efficiency for drip and we have 20% efficiency for flood irrigation, we could take that difference, that 60% difference, and use that as an index to influence the impact of water on soil degradation. Meaning that we have to identify a baseline value for the current soil loss, and then say, if we improve the efficiency of irrigation, so if you go from 20% to 80%, then we will see some reductions, more or less proportional, I'm not sure, but we will see some reductions in the soil loss due to the use of water and irrigation, inefficient irrigation. Make sense?
Yes, it does. Apart from, let's say, I'm just thinking about canals. If we're just talking about losses of water when we take it from one place to another. Basically,
Yes.
when we lose it, does it contribute to degradation of soil? Might, but then it might not.
It's more confined, right? Because that could be, if you have too much water, it spills over to the fields. But it's not a massive problem, I would guess. It's connected to the location where you have the canal. But what would be the most important impact is the flood irrigation as opposed to the drip irrigation, right? That's where you have a higher volume of water passing over soil and therefore carrying topsoil with it, right? With the water flow.
So shall we introduce different types of irrigation, or we just go with the efficiency? Or we just assign?
Up to you. I would say if we want to do a cost-benefit analysis, where we want to look at the cost of using one irrigation option as opposed to the other, it's better to have them separated, right? As one each. And then you can choose which technology you use for how much land. If instead you want to just look at for now the impact of efficiency, water that flows on soil, on degradation, then it's okay to run the policies. But if you want to look at and add to the model the different technologies, I've done that for other models. I can send you pieces of a model that you can use for that, and subscripts already built in, if you like, before in the next day or so that you can review it before the next session and maybe start working on some of the changes.
Yeah, that would be great. Yes, because I'm not
Okay.
very. Yeah, I don't have the numbers there.
Okay, we can start with the baseline numbers from international sources and then adjust it. Right? You can do that. Then, since it's almost time to take the next break, and then we have probably about another 40 minutes or so. What else, based on what we said, could be the policy story? What else do we need to modify? So, as we said, we have the potential to change land productivity directly based on the land use practices. We have the potential to change price. We have the potential to change labor intensity. We have now here adding the impact of the choice of irrigation options, of water management options on soil degradation, which makes so that we don't have a constant baseline for yield, but it will change and get possibly worse over time unless we improve the efficiency of irrigation. Is there anything else that is missing that you think should be added to tell the full story?
The prices?
The prices, yes. So, but that is an external discussion. And then we can say the premium price could be 10, 20, 30, 40%. So that could be an external variable, I assume. We may want to add the cost of certification in addition to the cost of changing practices. Maybe it costs more to use sustainable organic practices, or maybe it costs less. I'm not sure.
I don't know. Well, in some cases, it's pretty much the same. It's just a matter of using them correctly.
Meaning that you're saving money on chemical fertilizer, but you're spending something more on other inputs, I guess, right? So more or less, it's the same underlying cost per hectare. But some research that we could do before next week, I guess. So we're just listing the areas, right, that we could do more research on. Then Asel writes in the chat, climate change. So how do you think climate change can impact agriculture? We have rainfall here in this water model, right? So changes in rainfall will determine more or less needs for irrigation. What else?
And the yields probably, and the types of seeds that we have to use. So there will be droughts and the temperature rise, so there should be different.
So the temperature can have an impact on yield?
I think so.
Yeah, so you can consider that.
Well, at least the climate change can have an impact, and I think you have it somewhere, on extreme weather events like droughts and floods, and the drought is not a very good idea for agriculture.
Well, we have here in the water sketch, you see the indicator in the top right corner. It's called the share of stranded land.
Find water sketch, agriculture.
Yes.
Yeah.
So that is the amount of land that, it's called stranded, but it's the amount of land that even if you wanted to have irrigation, it's left without enough water because of changes in rainfall and at the same time, maybe a less than desired irrigation infrastructure.
It might also change the types of crops that you have to grow or you can grow, but this is a bit of a difficult analysis. I don't think we can go into that here.
Yes, but we do have 7 types of crops in the model, right? We have grains, wheat, barley, corn, potatoes, vegetables, and all the remaining ones. So in a scenario, this is, of course, more of a climate change scenario rather than a sustainable or organic scenario. We could decide to change the mix of crops if we see that there are some crops that require more or less water than others, and if we see that some crops may receive a higher premium price than others.
Can we add fruit? So, it was already demanded because we do have, they are heavily used in organic. So we have grains, wheat, barley, corn, potatoes, vegetables is fine. Remaining is fine. Can we add fruits perhaps? Because this is one of the policies.
If you have statistics, it could be added as an additional one, or if it's in remaining, we could extract it from remaining and make it a separate one.
I think that would be good because I don't think there are many places where you can, not a lot of variables you have to change this for, or how can you see where all of them are used?
No, so if we add a new one, we need to have the inputs for the crops or fruits in this case. We need to have the land, initial land productivity, and that's basically it. So these are the 2 main ones. Because with land and land productivity, we can estimate production, maybe water needs as what we will need.
But can you see where the I think we discussed, and I think you did it in your version of the model, which I always lose. You sent it already several times, but I don't know where I saved it. I think you said that you will add something to the variables that use subscripts, like crop type subscript. I don't know.
So I haven't done that yet. I think we discussed about that, but then after that discussion, I think it was said that all the changes were supposed to be made by you and IBEC, and I would facilitate. I made the changes that are related to, say, the underlying structure of the model. So the units, and a few other ones, if I remember well. But I haven't actually changed the subscripts for agriculture. I can do that, of course, if you want me to help. But I think we discussed.
But the names of the variables where the subscripts are used. For example, here we have water demand by crop type. Okay, I kind of guess that the subscripts are used here because it's by crop type, but it's not always the case.
Correct. No, I haven't changed the variable name. No, not yet. But that I can do. And I can also, I haven't done the full color coding exercise as well. So that I can also do, of course.
Okay, so we are still working with this model, so we don't switch to the other one.
Yeah, or whenever you can take a break, meaning that I would say when we are happy with the structure of the model and we start running simulations for the policy cases, that is a good time to start working on the name changes, the color coding, because we know that the equations don't change. We just run new scenarios. But if we work with models in parallel, then it's either difficult for me to introduce your changes, or it's difficult for you to identify where I've made my changes. So maybe by next week, if you're done with, say, the first 2 simulations, maybe one for energy, one for agriculture, then in the following week, starting Friday next week, you don't make any more change to the model. I make these modifications in variable names and color coding. And then once I'm done, you can start using my model. But knowing that it produces exactly the same results, but it just has some improvements on the variable names.
Okay, so then before we can, now for calculating the effect on employment and income, we need additionally in agriculture, soil erosion, we need to add it here. No, not here. Soil degradation. So this one be added.
Yes. And then the technologies for irrigation. And then we need to create an indicator that links the water losses in irrigation to the soil degradation index.
Types of irrigation. And you can send me this.
Yes, I would take this model and add the variables with the different types of irrigation.
Then we can basically start analyzing, right?
Yes, then we can start the simulations, even if you don't have all the specific data inputs, but we can do that.
Fruits as well.
So if you collect the data for fruits, then we can do the integration together next week.
The other thing, this is the crop part, and we have livestock part. We have the soil degradation already here. Do we have the runoff of manure, or do we need it? No, I don't think so.
We do have the total nitrogen from manure that is on pasture, so it's a proxy for that. Yes.
Here we need to take pigs of pasture.
yes, that the variable name changes. Yes.
And I remember I wanted to add intensive livestock growth. Intensive vertical, intensive keeping. Not only because this is one of the policies that could be used intensive, and this can be added where, but the pigs will be straight away into intensive, right?
It's based on the amount of land being used. I think it's in the we have pasture land stock in the pasture and grazing sketch. So we could have a reduction in the land use that shows that there's more intensive production, and this changes the land cover basically between pasture and crops.
But we take it off pasture then if it's intensive, or we just compress it.
Yeah, you see, we up to you. We can either put a higher number on the same land or keep the same number on less land. That would be part of the scenario design, I guess. Because you see, we have as a policy at the center, we have policy switch reduction in pasture land without changing the amount of animals. So there we assume we convert what we have into more intensive.
Oh, maybe that's what they meant. Because this is one of the things that I was wondering why was put in there. So maybe the reduction in pasture land is actually what they mean for intensive agriculture, but I don't see it in indicators. I don't see intensive agriculture, but this is maybe what is meant. Or maybe we can take it.
Well, we can add it anyway if we think it's a relevant intervention option. I would say in the context of the policy brief, let's keep it simple. We do the crops part. We can do a second one with the livestock. And then maybe we'll do a third one when we show the joint impacts of doing both at the same time. Just in interest of time, should we take a shorter 10-minute break now so that we then have another half an hour to maybe switch to have a similar discussion either for tourism or another sector? So then by the end of the hour, we have the list of tasks to do for next week to be able to then run the model and do the analysis, at least for 3 sectors.
A break until 16:30. Yes, I'm here as well. Let's see if the colleagues are. I also have another additional question. Now I'm also doing the industry for the green economy. And the questions there are related to determining the dependence of industrial development on electricity generation capacity.
Okay.
So the point is that what you have in the model is fully consistent with what there was in the program, but there is nothing the only thing is there in the industry is waste generation. And the another thing we have there is industry GDP. And do we need anything else we do have the productivity depending on transmission and distribution system, but not on electricity as such. Maybe Janebek is here. Maybe he can explain what they meant by this, because this is now I'm looking at it. What is it? Determining the dependence on industrial development and electricity generation. Well, what we do have here, we have the effect of energy price, but we don't have effect of actually there being enough energy or not enough energy. which I think was meant in this terms of reference.
Right, the difference between demand, right, the potential demand required to sustain growth and the actual availability of electricity and the intermittence in the availability of electricity. You see it that way?
Yes, in this case, we can have the point is that we don't have any disaggregation of different industries here. So we can just have the demand for electricity in industry, electricity intensity or whatever it's called, right? Per GDP unit, shall we say? Or per industrial GDP unit?
Yes, we do have energy demand for the industrial sector by energy source, right? In the energy demand sector.
In energy.
Yes. Also checking energy demand is disaggregated, looking at subscripts by residential, commercial, industrial, and transport. And we have coal, petroleum, electricity, natural gas, and biofuels and waste. So I think the main difference there would be between, let's say, what would be potentially required by the industry. So say in the model, we assume that demand and supply are the same, right? Because demand is the same as consumption. But it may well be that demand is actually higher than consumption because there is an unmet quantity that would be required by the industry. Make sense?
It does, but the point is, how do we know? I mean, we don't have, in the program at least, we don't have any indication of how fast they want industry to grow, or do we? I don't think we do. The only thing that they're talking about in the program is like waste and how do we make it more ecological and stuff.
Yes, I don't think there are targets on the growth per se. Let me check on my side what is the share of GDP that is industry, and if it's increasing in our case or not. Industry share in GDP. So the industry share in GDP, in the last simulation I have here, actually, let me look the last one we created last year.
I have here. This is what? Let's just leave one.
So this is the GDP, right? Look at the share of industry in GDP. So industry share in GDP. I think what we had before was a roughly constant value in the future. Maybe one of the goals is you see that at the top, right at the top in this sketch, industry share in GDP. Yeah, it declines now, but in the original simulations we had from last year, it stayed about constant. Maybe now we have changed other variables, and so we need a full recalibration. But maybe one of the goals could be to make it increase over time, because it has increased over time. And so maybe having more availability of electricity will allow the sector to grow more. But at the same time, looking at the other concerns, it will lead to higher environmental impacts. And so one goes hand in hand with the other, right? The availability of power and then the increase in production, leading to more waste generation, pollution, and so on. I would think.
In the absence of actual guidelines of how they want the industry to grow, would it be okay to look at, so we might look at if we don't do anything and if we don't any electricity capacity, can we see how the increase in agricultural industrial GDP will be sort of capped? Or, I mean, can we compare to scenarios when we have an abundant energy and energy shortages, and then see how that affects industry growth?
Yes. So I think it makes sense, meaning that on the one hand, the short-term shortages from, say, the distribution network and so on is captured in the model. So if we make changes to that, we will see productivity in the industrial sector increase, meaning that you can use existing production capacity better because you don't have these losses, the impact of losses. Then the other thing we could do is to say, especially in the new scenario where we expand the capacity of hydropower, if we have excess capacity in that case, we could make it a positive impact for the industry, showing that the industry could grow more because now you have more potential for electricity generation from the new large hydro project. So that could be added as well. It's a bit of a stretch, right? But if we say that, in fact, industry is not growing as much as desired because of the potential mismatch between the electricity required and the one available, when you add more and bring a project that creates more electricity, then you unlock the potential for industry to grow.
But this is what is going on in reality as well. Now, I mean, here to connect to electricity, you have to have a permission from the distribution network, because they actually know whether there is capacity or not, and it's very difficult to get one now. So we are already like stretching.
So it is difficult to get it because there isn't enough capacity in place to generate electricity to support the additional growth required.
Yes.
Okay. Yes. So that could happen. And then at the moment, we're assuming that you have demand for electricity that is driven by the historical trend, right? So we have the relationship historically that basically embed the fact that we're assuming a continuation of the same challenges. But if we are allowing electricity generation to grow more than demand, and demand in our case is consumption, so to grow more so as to accommodate the growing demand that is currently unmet, then this will provide a push to industrial production. So when we are simulating the expansion of the hydropower production capacity, and we see that the current demand is not enough, it's not requiring the full generation potential, we will have a positive impact on industrial production, so that we increase industrial activity, we increase GDP from industry, and as a result, we will see an increase in electricity demand up to the point where we use all the capacity that the new hydropower dam generates.
Okay, so do we need to add a connection there? Because there isn't one now. Look, the industry GDP is just growing indefinitely, even though I know we don't have enough. I have a feeling that it's not connected to, let's see.
So what happens now is that electricity supply is not constrained, right? So what happens now is that when GDP increases for industry or the commercial sector or agriculture, then the demand for electricity increases and the required power generation capacity goes up, right? If you go back to the total electricity generation, remember we compared the large hydropower generation in the same graph, and we said in the endogenous formulation, hydropower keeps increasing in the future because demand goes up. So we have that assumption that supply will always adjust to demand, basically. Now you have two factors to consider. One is that if we have a scenario where we use the endogenous formulation, this one that you're showing now, and we are not increasing generation anymore in the future, then we should reduce the potential for industry to grow. At the same time, after 2020, in this case, when we have the step increase in generation because we have the new project coming in that period, up to 2040 or so, we would do the opposite. We would say, okay, now that we have excess capacity, then we can increase industrial activity more. So if you put in the same graph, the total generation and total demand for generation, I think we looked at that before, but let's do that again.
Total generation and total...
And desired electricity generation in the top left corner. So if you compare these two, you see that the green line is above the blue one between 2020 and 2040. So this is where we could have an extra push for industrial activity, because the project we are introducing has capacity larger than what is the demand for power during these years. Then capacity is fully utilized from 2045. So this is the period when we could say, okay, then industry now can grow more because of the new project, an oversized project for 20 years. And at the same time, if we were to assume that we are not building that project, which should constrain industrial activity. So in the future, if we go with the green simulation, we should say we have extra industrial activity until 2040 compared to the older baseline. But then from 2045, we will have less industrial growth because the green line of electricity supply is lower than the blue one. So yes, we need to...
It's not connected. We have to connect it now. Now it only depends on quality of the distribution.
So before we had a one-way relationship, right? We said as long as there is GDP and there is demand, there will be supply, no constraints. We assume that supply will come online when there is demand. But at the moment, we're introducing a different set of causal relations. We are saying that it's not necessarily the case if the starting point for us is the project is built or not. So we are saying it's not necessarily the case that if there is demand, there is also supply. These are two different choices. So we need to add a feedback that will work as a balancing loop in a way. And we need to calculate an electricity demand-supply ratio so that we can see that we have oversupply until 2045 and undersupply after 2045. And that indicator can be used to affect productivity and production. Are you following? Yes?
Yes. I'm just thinking where we add it.
So this is, in this case, we can do a ratio between the desired electricity generation and total electricity generation. Or the other way around, it's generation divided by desired generation. When the value is higher than 1, is oversupply. When the value is lower than 1, is undersupply.
Shall we? We are not changing anything apart from that?
No, just adding the new variable, yes.
How do we
can say electricity demand and supply ratio. Okay, so I would make this generation divided by demand or desired value, the other way around. It's easier to understand that when the value is higher than 1, then we have oversupply.
And that would be dimensionless, right?
Dimensionless, yes. So if you run the model now, I know we have it set up for agriculture. But
so what happened? This is an error.
We may have made changes to some equations. Click on check syntax and see what it says. Okay. Click yes.
I put first erosion index.
Just confirm for now. Yeah, I think so. Yes, it's fine.
Do you think it's going to run now?
Yes. Okay, check the electricity demand and supply ratio.
So then this is...
we will need to see what 1 is, but I guess it's around the initial value. Yeah. Yes, so we see we have some oversupply in the early years, definitely up to 2040 with the new project. And then we have undersupply afterwards, right? Now, with this in mind, an additional consideration we can make to building this feedback loop is if you're not going to build a large hydropower project, other options would be considered or not, because we can make so in the model that if you don't do hydropower, then other options like coal or gas, other options would be chosen by default. Or do you actually want to show that if you don't do the hydropower, there will be constraints to power supply, and so you have economic impacts emerging?
I think we would. I would do somewhat the choice of 3. First is we build large hydro. Second, we import, because we're talking about industry. It's not going to be enough to build small hydro. This is not on the scale. Or, and maybe together with all of these, we increase energy efficiency of industry, which would be actually the first choice.
So that you can avoid expanding capacity a lot, yes.
So the first choice would be increasing energy efficiency.
Yeah, so this means that we do not have to make it fully endogenous, right? We can leave it as is to say, in one scenario, look, there is a power shortage. And then second scenario, this is first option to address the problem. We improve efficiency, so we reduce demand. Then there is a second option where we say we import with the price of imports, of course. And so we build up the story in 3-4 different scenarios. So we don't have to assume that the model fixes the problem on its own. So I have my answer. So going back to the approach we use for agriculture, what is the core policy question and policy message that you want to address in this case for industry?
What I want to address here. This is very interesting question.
And it's because we're talking about model changes, but I want to make sure that by the end of the call, we're very clear on what is the type of analysis we want to perform.
Green interventions on the sector. The point is that they want everywhere. I think what is wanted is to show which policies would lead to increase of employment and GDP while looking at possible negative effects on environment, I think, and other sectors, right? So, the main question of the model as such is how do we increase GDP and not damage anything else?
Right. So in a way, you would want to show, if we start from the electricity argument, that there is an unmet demand, that if we address it, it would allow the industry to grow more. But at the same time, we need to decide carefully what are the options for that, if it's hydropower, imports, and so on, because they have different consequences on, say, emissions and so on. And at the same time, then we need to keep track of the consequences of growth. That could be the pollution and so on. Okay.
Yeah, on the pollution, we do have something actually here, but this is not domestic waste generation.
Not too much. Yes,
But this is
we have
waste.
a few data points for different types of waste, but yes, if we change GDP, the waste generation will change as well.
And we don't have. Do we have pollution? Air pollution? Somewhere?
No, because it's a localized local concentration value, right?
But here we have. But this is for energy.
And what we're also missing is the policies for how to treat and deal with the waste for industry. So maybe it would be good to add some more interventions there, like options to reduce waste generation, options to recycle and reuse waste, and then add the cost of waste management. But these are exactly the areas for which we couldn't find data when we worked on the model. We have some flows, but nothing on interventions. But again, it's something that we can do research on and see if we can improve it.
Okay, so then we have 8 minutes.
So let's summarize the three main policy assessments that we want to do, so that we summarize them. We can write them down in bullet points, so that it's easy for everyone to pick it up and decide how to move ahead. So we said we have energy, agriculture, and industry at the moment. Can we summarize the approach, the policy approach and analysis for each? What we want to do for energy, what policy change and key indicators for the analysis, and same for the other two.
Oh Jesus, I already forgot. So what do we want to see, right? For energy, we wanted to see.
We can start with industry and agriculture if it's clearer, and then we go to energy last.
Agriculture. What policies would and GDP, right? And industry policies. What is the influence of energy of different GDP and something like that? Does it make sense? So what's the influence of different energy sector development scenarios on industrial GDP and employment, and which policies maximize GDP and employment to be completely understood by everybody, while keeping possible negative effects at minimum? What do you think?
Fine with me. Up to you to decide among all the participants if there is enough detail in this statement to remember what are the key areas. Maybe we can list one of the two intervention options that we said we would test. So for industry is expanding power generation capacity with hydro.
No, first is business as usual.
Yes.
Nothing happened. Second, expansion of Lloyd. Second is energy efficiency measures. Expansion of hydro. Sorry. Business as usual. I'm not sure if I should do that, but there's another option. Then what policy would increase agriculture while keeping possible negative effects in minimum? Negative effects here would be inflation. Organic farming, they have like 3% in what is one of the goals. I have a question. I mean, what I don't like about doing all of the changes at once and seeing the effect of the green economy model as one, we've done everything, because it's never going to happen. From the other point of view, to look at each and single intervention, so this can be also quite a lot of them. Look, I mean, if we just look at this and then this and that, this is like
we always need to look at interventions one by one to understand the net impact of each, and then we need to combine the ones that create synergy or the ones that create trade-offs, especially if the goal is to create a policy package, right? Then we need to test the whole package, but we can certainly test them in isolation, or at least we have to give an idea of what is the net impact of each.
Rather the other way around. I don't know whether that is everything. I think I forgot half what we discussed. Yes, and we were talking about thermal prices. This is for energy. What is the cost? Well, this is not what we do for energy, but however, in energy we have still the same question: what do we do? Which is related actually to industry. What do we do in energy so that we have GDP and employment maximized?
Yes, it's about the same. I guess it's the same in a way that we can look at a combination of extra capacity, efficiency, and the potential job creation in both cases, resulting economic growth. And apologies in advance from my side because I need to leave in 2 minutes very soon.
So let me just save that. Can you perhaps add what you remember? Or
from my side, it's about the same. Yes.
Mm-hmm.
Nothing very different. I agree, energy and industry are very similar. So if you do energy first, we could say, let's look at the cross-sectoral impacts, for instance, on industry to build a story. And so energy and industry are certainly related, agriculture a bit less in this case. For agriculture, you started mentioning the livestock component. I'm wondering whether we should keep them together or separate.
Livestock
like to have two policy briefs, one on crops and one on livestock, or one with both.
Okay, if I remember anything else, I'll add it and then I send it to you, well, to everybody by tomorrow, maybe to comment. And that would be it for today, since you have to leave. Thank you very much for your guidance today. And then how do we build I look for all of the data until the next Thursday, and then we'll look at it.
Yes, in the meantime, it would be good to be able to run the model either before or during the session next week for some of these scenarios. I will send you input on the irrigation. So if you send me the model you have now, I will add the irrigation aspects. And then I've noted that once we have done the simulation, so the model is complete, then I can work on the renaming of the variables with subscripts and the color coding. But I can certainly work on the irrigation part. And if you have questions, depending on the data you find and so on, write me anytime before Thursday. Let's not wait for Thursday.
Okay, so I've sent the model there.
Yes.
I'll leave it there for a couple of minutes so you can all download it. Otherwise, colleagues, if there are no more questions, then that is all from my side.
Yes.
Okay, great. Next week. Thanks a lot.
Thank you. Thank you, Roland. Bye, everyone.